Okay, part two is just about Coulomb's law. So we're just going to go over the equation and how to do it. It's going to be somewhat familiar because it's going to look a lot like the gravitational law. So we've already covered that. So you should be able to do very similar things with it. So Coulomb's law is the force law for charged particles or charged objects. And so the electrostatic, and by static we mean things that are holding still. So these charges are not moving around from one object to another. So the electrostatic force varies directly as the product of their charges. Now, Q here represents the amount of charge. Okay, so I've got Q1 and Q2. And so they're multiplied by each other, the product of their charges, inversely as the square of the separation of the distance. So we've got distance squared. So this probably looks a lot like the gravitational law, where you have usually m1, m2 over the distance squared. Now, if you'll notice, there's also a constant here, which is k, but it's much nicer than the gravitational one. So k is the proportionality constant, and it's a really nice number, 9 times 10 to the 9th newtons meters squared over Coulomb squared. And so that helps convert the units to the proper amount of newtons. So you've got to make sure you put it in there. If you don't have k, then you won't have the right force in newtons. And of course, this works with positive charges or negative charges when they have like signs. Okay, so two positives or two negatives, then it's repulsive. When they have unlike signs, then it's attractive. Okay, so let's do a little problem. What's the force between two small charged spheres? Q1 is 3 times 10 to the minus 4th coulombs. Q2 is 8 times 10 to the minus 6th coulombs. And by the way, the minus 6 there, of course, is a micro, it's called. So we might call that a microcoulomb. Micro means 1/1,000,000th. Okay, and electric charges are often quite small. The distance is going to be only 2 centimeters between these two spheres. Okay, so let's find the charge. Let's find the force. Okay, so we're going to put it in. Force is equal to K, so don't forget your K, 9 times 10 to the 9th newtons meters squared over Coulomb squared times the two charges, 3 times 10 to the minus 4. Oh my goodness gracious. And that, of course, is in coulombs. And then we have 8 times 10 to the minus 6th coulombs. Maybe I should just type this in to start with. Okay, and then we've got it divided by 2 centimeters. So I'm going to put that 2 times 10 to the minus 2 meters and square it. Okay, so like with gravity, I'm going to take all the real parts, okay, and then do the exponent parts separately. Easiest way to do it. So I'm going to do 9 times 3 times 8 divided by 2 times 2. And then I'm going to have all my exponent parts. So 10 to the 9th, 10 to the minus 4, 10 to the minus 6. And don't forget, it's squared on the bottom. So it's going to be 10 to the minus 2 times 10 to the minus 2. Okay, so now this makes it really easy because I can just do this part in my calculator or my head. And so we're going to have 12 times 9. Okay, so I get 108. Oops, hold on. I think I canceled wrong there. 8 over 4 is 2, so that's 6 times 9, 56. All right, sorry about that. I was doing it in my head. And then on this side, we're going to have 9 minus 4 minus 6. So that's 9 minus 10. So that's going to be 10 to the minus 1 on the numerator. And on the denominator, we're going to have 10 to the minus 4. Remember, of course, you are subtracting when you're dividing by these exponents. So that's going to be minus 1 minus a minus 4, or minus 1 plus 4, which makes positive 3. Okay, so if I did my math right, this becomes 56 times 10 to the third, or 56,000. And since it's a force, it should come out in newtons. Just to make sure, let's check our units. So how does it get to come out to you newtons? Well, you've got coulombs squared here. It cancels the coulombs. You've got meters squared here, which cancels the meters. And then all you're left with is newtons. Okay, so that's why you have to have the constant in there, is to make sure you get the right units out. Okay, so 56,000 newtons. That's a really big force from those tiny little charges. But that's the thing. The electrostatic force is really big. Gravity, you need a whole planet to really notice it much. But because the electrostatic constant is 9 times 10 to the 9th, that's 9 billion, then what you get is a very large force, even for what seem to be small amounts of charge. Okay, so a very big force. All right, so that should help you figure out that. Now, of course, the Coulomb's law, it does have that inversion relationship to the distance, right? So it's 1 over the distance squared. So it's called an inverse square law, again, like we talked about with gravity. And so when they're twice as far apart, 2 particles will experience 1, right? So 1 over the distance squared. So 1 over 2 times the distance squared is going to be 1/4 of whatever you had before. Right? So so when you double it, it's 1/4 as much. So should be answer B, 1/4 as strong. And of course, if the distance was 3 times greater, it would be 1/9, right? 1 over 3 squared. So just like there was questions on the test and the homework about the inverse square law for gravity, those will come up again on this next test for electrostatics. Okay, so what are the differences and similarities between the gravitational force and the electrical forces? Well, gravity only attracts. We have not discovered anti-gravity, whereas electricity can attract and repel. The forces act between things that are not in contact with each other. That used to be called action at a distance. And it was very impressive to people, who first were playing around with electricity. So the Greeks very early on found that they could rub a piece of amber and it would attract small pieces of paper. The forces act in a straight line direction. And there is a force field that we'll be looking at. So there was a gravitational force field. We talked a little bit about that, but we're going to talk more about the electric field. Okay, and let's see. When you, there are some fun FET simulations, so I'll put those on the website. So let me see if I can shift to those. So these are just fun simulations that you can play around with. So these FET simulations, I don't know if you've ever used them in school before. One of them is on Coulomb's law. And so in that case, the idea is that you can have different amounts of charge. So like this is -4 microcoulombs. So again, that mu shape is called micro. That means 10 to the -6. And so this is -4 millionth of a coulomb of charge. And here we've got 8 microcoulombs. And you can change that. So the problem we just did, we could have done the problem we just did. I'm not sure we actually can on this because they only are in microcoulombs. Anyway, but the idea is that you can play around with this. And so you can have different amounts of charge. And then you can vary the distance that they're at. So you can move them around. And so then up above, they've got their forces. So right now, the force is 149 newtons of force on each one. Bring them closer together, the force is greater. Further apart, the force is less. So if you want to practice your Coulomb's law, you can pick out some charges and do the math and then check to see here if you got it correct. And let's see, we can change this. Should be able to change it to a centimeter scale, maybe not. Let's see. That's kind of weird. Okay. Anyway, it's in inches. Well, that's good. Anyway, so anyway, set up for the force value if you want to see the forces, right? So there's a click there. Okay, another one that's in here is just a fun charging one. So we're going to be talking about charging later. So so we'll come back to this one. Okay, and another one is, that's called balloons and static electricity. Another one is John Travoltage. So yeah, so there's the website fet.colorado.edu, and they have all sorts of simulations for students and teachers to play around with. Okay, so we'll get back to the other two after we talk about charging.